So I'm going to talk about black hole complementarity and draw some useful distinctions, hopefully useful distinctions regarding black hole complementarity. But let's begin with asking why we should talk about this. I don't think anybody here needs persuasion that the black hole information paradox has become a central problem in modern theoretical physics. If you need to be convinced of that, you can just go on Google Scholar and type in black hole information paradox and see the piles of papers that have been written on this topic recently. And what black hole complementarity is an influential set of ideas that have emerged in response to this paradox. But it's not always clear what people mean by that term and what its relation is to the information paradox. So my goal here is to hopefully add some clarity to that discussion. But before we get to black hole complementarity, we need to talk a little bit about the black hole information paradox. The setup is an evaporating black hole. So what you see is the Penrose diagram for an evaporating black hole with three typical Cauchy slices delineated for you. There's a slice that is before the formation of the black hole. There is one slice during the evaporation of the black hole, and there is one slice after evaporation. Now, in this context, at least two different kinds of black hole information paradoxes have been distinguished between. One is called the total evaporation paradox, and that is what you would usually hear in popular presentations of the black hole information paradox, which is the idea that when a black hole evaporates away, all the information that fell into it somehow disappears. Many have argued that the case for that particular problem being really paradoxical is not very persuasive. The other paradox that has been articulated in this area is the page-time paradox. By the way, the distinction between these two problems was drawn by David Wallace in his 2018 paper, Why Black Hole Information Loss is Paradoxical. Now, we will focus on the page-time paradox because the case for it being paradoxical is much more persuasive, and also because this is the context in which the black hole complementarity literature operates. So what is the page-time paradox? It's a contradiction between the following three statements. The first statement is that black hole evaporation is unitary. The second statement is essentially the claim that the black hole is a quantum mechanical and statistical mechanical object. Consequently, its microcanonical entropy has to be an upper bound to its fine-grained entropy, or in the language of the black holes, its Bekenstein-Hawking entropy has to be an upper bound to its von Neumann entropy. And the third statement of the trilemma is that Hawking radiation is perfectly thermal throughout evaporation. All these three can be justified, have independent justifications, more or less. I'm not going to articulate those arguments here, but these papers would be a helpful place to start. So what is the problem? What is the contradiction between these three claims? So let's look at an entropy curve. Imagine that the y-axis is the entropy of the black hole. It could also be the entropy of the radiation. And the x-axis is the time. So suppose black hole evaporation is unitary and Hawking radiation is always thermal. Well, what does that tell you? Well, it tells you that the entropy of the radiation is going to increase continuously. So you can imagine enveloping a black hole by a huge Dyson sphere and collecting all the radiation that's coming out of it and seeing whether it's thermal or not. And if Hawking is right, then it should always be thermal. And so its entropy should go up continuously along this line over here. And because black hole evaporation is unitary, the entropy of the radiation has to be equal to the entropy of the black hole. The von Neumann entropy of the radiation has to be equal to the von Neumann entropy of the black hole. And this is simply because entanglement entropy of one subsystem is equal to another subsystem that is entangled with. So if you have two subsystems, the entanglement entropy of one is equal to the entanglement entropy of the other. And if the black hole is evaporating unitarily and it's a statistical mechanical object, well, it has to be the case that its entropy, its von Neumann entropy starts decreasing at some point. Because remember, the statistical mechanical objects have their microcanonical entropy as an upper bound. And as a black hole is evaporating, its area is decreasing. And the Bekenstein-Hawking entropy is proportional to the area. And so it has to be the case that at some point, the von Neumann entropy has to start decreasing. Intuitively, this is simply the idea that any information that falls into the black hole has to start coming out at some point. So obviously, you can't have an entropy curve that's increasing continuously like this and also decreasing at some point. So we have a contradiction, and that's the paradox. Moreover, Don Page has articulated that this entropy curve is more likely is likely to have the following shape and almost precisely increase continuously until halfway point and start decreasing at that point. And that halfway point through the evaporation of the black hole is called the Page time, or the point at which the entropy curve changes direction. Okay, so we have a paradox on the table. Now, what do we do? So here's the plan for the rest of the paper. First, I will tell you how black hole complementarity can be seen as a response to the paradox that I have just delineated. By the way, a word of clarification, by complementarity, I'm going to mean black hole complementarity throughout this paper, throughout this presentation. Of course, black hole complementarity was inspired by quantum complementarity, the idea of Niels Bohr. The relation between the two is not very clear. I'll say a word about that later, but everywhere else, when I say complementarity, I mean black hole complementarity. So after I have said how complementarity emerges as a response to the paradox, or during that whole process, I will also articulate the central distinction that I'm presenting here, which is between operational and descriptive complementarity. This is a distinction which, to the best of my knowledge, has not been drawn clearly before. I'll also argue that complementarity is best understood as a claim about consistency. And I will argue that the operational way of understanding complementarity has been much more successful than a descriptive way of articulating complementarity. And finally, I will say what directions one can go depending on one's philosophical commitments, either as scientific realists or some kind of instrumentalist about scientific theories. Okay, so the Page time paradox gave us an inconsistency, but what do we do with an inconsistency? In general, if we have an inconsistency, then that suggests that we have to give up one of the commitments in the set of statements that create a contradiction. But which one should we give up, and what does that mean, giving up? What does giving up one of them mean? But before we even get there, it's worth asking whether we should give up any of them at all. So surprisingly enough, science often goes on completely successfully, even when it has some inconsistency within it. Among philosophers of physics, it's a point of pain that the quantum measurement problem has not received much attention in the physics literature. And at least on some base of understanding the quantum measurement problem, it's a straightforward inconsistency within the theory, but the quantum mechanical calculations seem to be immensely successful. So science has managed to go on despite there being this inconsistency in its formulation. There are many other examples. There's this nice book by Peter Vickers called Understanding Inconsistent Science, where he goes through many examples where science has carried on in the face of an inconsistency. So is this one such situation where we have an inconsistency, but perhaps it doesn't impede the development of the theory? Well, to see whether that is the case, a natural question to ask is whether we can get an empirically observable contradiction from this collection of statements. Some kind of experiment that one observer can do, which will result in a direct violation of quantum mechanics. So let's just imagine a quick thought experiment to warm up. So let's say you have an observer, Bob. He's collecting all the radiation coming from a black hole. By the way, just nomenclature, the person hovering outside the black hole will always be called Bob, and the person falling into the black hole will always be called Alice, at least in this presentation. So Bob is hovering outside the black hole, and he's collecting all the radiation that's coming from it. He waits past the page time. He sees that his radiation deviates from thermality, and this suggests to him that there's something that has gone wrong with Hawking's calculations near the horizon, right? Because Hawking's calculation told us that the radiation should always be thermal, but Bob is seeing a deviation from thermality. So he wants to go to the near horizon area and examine what's happening there and see whether he can get a clear violation of quantum mechanics there. Can he do this experiment? No, not really, because in order to hover right above the horizon of a black hole, he would need to sustain Planck scale accelerations. So he couldn't do this experiment if he couldn't access Planck scale physics. Well, you might say, okay, that was an idea, but surely we can imagine a cleverer experiment, some more sophisticated experiment that will allow an observer to extract some kind of violation of quantum mechanics. But this is where the first principle of complementarity, what I call the operational principle of complementarity, comes in, and it says no. So let me just read out the statement as I've formulated it. No experiment attempting to create the observation of a direct contradiction of the rules of quantum mechanics by a single observer near or in black holes will succeed, as long as that observer cannot empirically access Planck scale physics. This particular way of saying it has not been precisely said before, but statements more or less to the same effect can be found in the references that I've given below there. I call this an operational complementarity principle, an operational principle, because it's making essential reference to the capabilities of an observer. That's what I mean by operational. I don't mean something quite sophisticated as, say, Percy Bridgman's idea of what it means to be operational. This is my use of the word operational here is in keeping with the language that's commonly adopted in this literature. Okay, so we're going to investigate the power of the operational principle of complementarity in a minute. But before we get there, I need to do a little bit more stage setting. And let me just briefly introduce what gets called the stretched horizon. A useful way to imagine the stretched horizon is this quantum mechanical surface that's one Planck length above the true horizon. The reason for its existence can be argued using two of the statements that form the problematic of the page-time paradox. The first is that black hole evaporation is unitary. So if we want a unitary black hole, this means that we need a field theory on the exterior that has a boundary strictly above the horizon, which can absorb and re-emit information crossing it. Because if we did not have some way of the information sort of coming back into the exterior, then we couldn't maintain unitarity. The second thing is the fact that the quantum mechanics, the black hole is statistical mechanical, and so the field theory should attribute an entropy that is bounded about by the Bekenstein-Hawking entropy. As it turns out, you can satisfy both these two requirements by locating a boundary surface located one Planck length above the horizon. And this is the stretched horizon. In the classical limit, this becomes what is the membrane of the membrane paradigm. Or another way of thinking about the stretched horizon is as quantizing the membrane of the membrane paradigm. So what is this membrane paradigm I'm talking about? So in the 80s, people like Price, Thorne, Blanford, these physicists were trying to figure out how to think about the black hole as an astrophysical object, really just as another star in the sky. before that, mathematically, a black hole was being thought of as just this arrangement of space-time instead of a real physical entity out there in the sky. And when they were trying to do calculations of how this entity will interact with its external degrees of freedoms, such as electromagnetic fields or mechanical forces, they realized that mathematically, the space-time description in terms of the metric structure can be translated into imagining that there's this surface, a membrane, just above the true horizon, which has real mechanical properties, which can carry currents, which can support charges, carry mechanical oscillations. And you could translate between them to, just as a matter of mathematical equivalence between these two descriptions, a space-time description and a membrane description. Now, the stretched horizon can be thought of as just the quantization of the classical membrane. So it's not something quite so alien that comes up only in quantum mechanics. It has a precedent in classical GR as well. Okay, so let's go back to complementarity. So let's see how operational complementarity works or what it's useful for. We have this following thought experiment. Bob is hovering outside the black hole. Alice is falling into the black hole. So we know from classical general relativity that Alice is going to experience a smooth crossing at the horizon. However, from Bob's perspective, what he's going to see is that Alice is going to hit the stretched horizon and then disperse on it. Because from his perspective, the black hole is a unitary object and the stretched horizon is this boundary around that. So it seems as if there's a contradiction here, because it seems like there should be a fact about whether Alice arrives at the crossing or not. But can Bob really empirically investigate whether there's a violation of quantum mechanics or some other principle of physics here? Well, in order to do that, he would have to resolve Planck scale effects, because the distance between the stretched horizon and the true horizon is 1 Planck length. That means if he wants to probe what happens to Alice as she crosses the stretched horizon, then he has to do that before she crosses the true horizon. And so he will have to send in modes of Planck's scale of Planck length in order to resolve what's happening there, if it even makes sense to talk about modes, field modes at that length scale. Similarly, if they prearrange, so if Bob tells Alice, okay, as soon as you cross the stretched horizon, just send me a signal and I will know that you safely made it past the stretched horizon. And so I'll know there's something wrong with my picture, which describes you as being dispersed on the stretched horizon. Well, she'll have to send that signal before she crosses the true horizon, because otherwise the signal won't come out, of course. And so she'll have really just 1 Planck distance to cover before in which she can send out that signal, and consequently her signal will have to be Planck frequency. So you can see that this is consistent with the way I formulated operational complementarity, because it said you can't have a violation of quantum mechanics as long as you don't have access to Planck scale physics. So this restriction on Planck scale physics is preventing Bob from seeing any potential violation, even though at some level of description, it seems like there must be some contradiction going on. So if you are uncomfortable with operationalism, as many of us rightfully are, there are powerful sets of arguments articulated by philosophers against operationalism or instrumentalism in science. And for example, one quick argument is empirical apparatuses and human beings and observers, they're all bits of physics. They're all constituted by physical objects. So it seems odd that there should be some separate set of principles that will apply to us. So one might want to look for a principle of complementarity that's not operational. In other words, that constrains not capabilities of observers, but representations of the world, or constrains statements about the way the world is. So is there something like that we can do here? Is there some principle of complementarity that constrains two different descriptions of the world? There are two natural candidate descriptions here. So let me say that now. So consider the following two low energy quantum mechanical descriptions. We have already introduced them more or less, but let me just say a little bit more about them. The first is the exterior description. Let's imagine this is a description that includes degrees of freedom outside the horizon, and the stretched horizon is the boundary of this description. The black hole evolves unitarily, and it's a statistical mechanical object. This is the description that's appropriate for hovering observers, but the description itself is independent of any appeal to observers. Similarly, there's an infalling description, which includes degrees of freedom on the outside, but also inside the horizon, minus the singularity, of course. And it does not include the stretched horizon. And this is a description that's appropriate for infalling observers. So you have these two descriptions of a black hole. So let's try this complementarity principle. So this is what I call descriptive complementarity. And this simply says that these two descriptions are descriptively consistent and with quantum mechanics. By descriptively consistent, what I mean is that they can be simultaneously true or accurate representations of the way the world is, while being consistent with quantum mechanics. This is in distinction with operational consistency, which was the previous complementarity principle. And that was about the consistency of observations of single observers. Here we are really taking representations of the world and seeing if two different descriptions can simultaneously be considered to be accurate representations of the world. In the interest of time, I'm not going to say too much about holography, but in my thought is that holography, at least on some way of reading it, could be seen as a principle of descriptive complementarity, because if you have two dual descriptions and they're both simultaneously accurate, then they're of course consistent. A small note of caution, this is where the remark about Bohr comes back in. So Niels Bohr's complementarity seems like it's a descriptive principle of complementarity, because in that context in quantum mechanics, Niels Bohr talked about being able to use only one of two different descriptions depending on the context. But it's not descriptive in the way I'm construing descriptive complementarity, because Bohr did not take those descriptions to be representationally serious. He said, depending on your experimental context, you can use either one description or the other. And so that's an operational restriction, because depending on which kind of observer you are, you can use one or the other description. But it's not saying that if you have two different descriptions, they can both be simultaneously true. One more point of clarification on the literature. So in this literature, the name complementarity is sometimes used to refer to the claim that there is this exterior description with a stretched horizon, or there is a stretched horizon. The existence of the stretched horizon, I think, follows just from straightforward accepted physics. So I don't think it's worth elevating that claim to a principle and examining it. However, the claim about consistency, about an exterior description being consistent with an infalling description, or there being no operational contradictions here, that kind of claim, I think, is a non-trivial additional claim and deserves to be elevated to a separate principle. So, and moreover, in the literature, I don't think people have been very clear about what notion of consistency they've been using. And hopefully, drawing a distinction here could be useful. Okay, let's get back to the main narrative. So let's go back to this thought experiment with Alice crossing the horizon and Bob hovering above it. We saw that operational complementarity was vindicated in that context because Bob could not perform any experiment that could empirically detect a contradiction. Now let's see whether the descriptive principle of complementarity can also successfully resolve this problem. So in the exterior description, Alice hits the stretched horizon and scrambles on it. And the infalling description, Alice continues through the horizon smoothly. But notice that these two descriptions are mathematically equivalent. You can see this even from just classical general relativity. And classical GR, in infalling coordinates, Alice will just smoothly cross the horizon. In Schwarzschild coordinates, Alice will approach the horizon closer and closer and closer, but won't ever cross the horizon in finite time. But those two descriptions can be translated among each other by just changing coordinates. A similar thing can be said in quantum mechanics, where you can take the description of Alice falling into the horizon and then just do a coordinate change and have that be described by Bob as Alice being dispersed on the stretched horizon. So the descriptive, it seems to be the case that these two descriptions can be simultaneously true representations of the way the world is. So if you're keeping score, as we'll start keeping score now, both the operational and descriptive complementarity principles are vindicated here. They seem to be able to be true. And if you have an allergy to operational principles, then you might be more inclined to accepting the descriptive principle of complementarity, because philosophically it seems more attractive. However, this situation is going to change now. An operational principle is going to start pulling ahead. So let's consider another thought experiment. And this is sometimes called the cloning paradox here. So just as in the previous case, Alice is falling into the black hole. She experiences a smooth crossing. And from Bob's perspective, the black hole is a unitary object. So Alice hits and disperses on the stretched horizon. However, as we noted earlier, the information has to start coming out at some point. If black hole evaporation is unitary, the black hole is statistical mechanical. And so after the page time, Alice, or at least the information contained in the degrees of freedom that constituted Alice, will have to start coming out in the Hawking radiation after the page time. But then we seem to have a problem, because if Alice continues smoothly, then the information constituting her is in the interior, while at the same time, it's also in the radiation. So you can consider a Cauchy slice like this, and you'll see that Alice exists both in the interior and in the radiation. And this seems to be a straightforward violation of the no cloning theorem, which tells you that you can't have a general quantum mechanical process that takes an arbitrary quantum state and creates two copies of it. And that seems to be what's happening here, because there's no restriction on what Alice is. So note that the descriptive principle of complementarity just fails here. The descriptive principle does not rule out the possibility that there are such foliations that are smooth across the horizon. And it just is the fact that these foliations contain a clone of Alice. And so if we take both the exterior description and the infalling description as successful representations of the way the world is, then we have a straightforward violation of quantum mechanics. And so this is inconsistent with descriptive complementarity. But the operational principle succeeds here. So this was discussed in Jonathan Bain's talk earlier, but just to quickly recap, the idea is that you can't do any experiment that for a single observer can measure or notice or observe the clone. So let's imagine how that might go. So Alice jumps into the black hole. The information constituting her comes out in the radiation after a while. Bob collects this radiation, and then he jumps back into the black hole. He jumps into the black hole following Alice. And they have pre-arranged that Alice is going to send him a message with her information as soon as she crosses the black hole. So earlier, we were thinking of Alice herself being cloned. In this context, let's imagine that we are just concerned with one quantum bit, one qubit that Alice is carrying, and we want to check whether that single quantum bit has been cloned, because even that would be enough to violate quantum mechanics. So Alice and Bob agree that Alice is going to send the qubit to Bob via a photon after she jumps in, and then Bob's going to wait for the information to come out, and then he's going to jump in after Alice, compare the information that he has received in the radiation with the message that Alice has sent him, and if he can see that the two quantum bits are the same, he would have observed a violation of the no cloning theorem. And consequently, the operational principle would be false. But as it turns out, and in this sort of remarkable result by Hayden and Preskill, building on this work by Susskind and Thurlasius, it's not possible for Bob to do this before he crashes into the singularity. As it turns out, the shortest time before which Bob can acquire the information in the radiation is order m log m. So Hayden and Preskill argued that after a page time, the black hole becomes what they call an information mirror. That is, any information that falls into the black hole comes back in the radiation very quickly. So just to give you a flavor of what very quickly means, the evaporation time of a solar mass black hole is on the order of 10 to the 63 years. The time scale on which an information radiates back out after the page time is on the order of milliseconds, right? So if you put information into a black hole after the page time, it's going to come back right back at you. But as it turns out, even this extremely short time is too long for Alice to send the information to Bob. So as Hayden and Preskill argue, this is exactly the same time scale within which Alice has to send Bob the signal if he's able to receive it before he hits the singularity. Or to be a bit more precise, the time difference between when Bob receives the information and jumps in and when Alice can send the message will have to be on the order of the Planck time. And so consequently, Alice would have to send her information in modes of Planck frequency. And so even in this extremely forgiving scenario, Bob is unable, or there's no observer here who can detect a violation of the no cloning theorem. So if we're keeping score here, the operational principle leads 2-1. The other thought experiment here, and I'll go through this quickly in the interest of time, is the violation of entanglement monogamy. Jonathan Bain also discussed this. So the idea is that if you call the radiation that comes out of the black hole before the page time early radiation, and the radiation that comes after the page time late radiation, then it must be the case that the early and late radiation must be highly entangled, because the radiation is starting to purify, and so the only way that can happen is if there's a large amount of entanglement. However, Hawking's calculation tells us that the radiation, the late radiation, has to be entangled with modes across the horizon. So it seems like the late radiation is highly entangled both with the early radiation and with modes across the horizon. And this seems to be a straightforward violation of entanglement monogamy, which says that no single quantum system can be highly entangled with two different quantum systems. Note that descriptive complementarity fails again here, because you can easily imagine a foliation which contains this entanglement monogamy violating state, where you have the late radiation, the early radiation, and modes across the horizon. As it turns out, you can't do an experiment, however, that can detect this violation of monogamy. And the idea was presented by Harlow and Hayden in their 2013 paper, where they argued that there's a computational barrier to doing this task. That is, in order to do this
experiment, one would have to distill the entanglement emerging from the black hole and then carry that distilled state into the black hole and compare across the horizon. But as it turns out, quantum computational complexity theory presents a barrier to performing this distillation task within the lifetime of the black hole. Not everybody was convinced by this result. Potential loopholes were pointed out, but as it turns out, those loopholes have barriers of their own. And interestingly enough, this kind of dialectic, so first of all, we see that operational complementarity is succeeding here because operational complementarity said that you can't have an empirical observation of a violation of quantum mechanics. And as it turns out, even there's a computational barrier to this. And interestingly, there's an analogy with dialectics earlier in the history of science, right? If you think about, say, a perpetual motion machine, what would happen is that there was this principle that you can't build perpetual motion machines, which is a sort of an operational principle because it places restrictions on the capabilities of experimenters. And the way the dialectic would proceed was someone would come up with a design for a perpetual motion machine, but someone else would come along and point out some subtle flaw in that design, right? Some way in which that machine is losing entropy or energy, gaining entropy or losing energy. Or another analogy here is with the Einstein-Bohr debates, right? Where Einstein would perhaps come up with some idea that would show some kind of violation of the uncertainty principle. By the way, I'm going on very popular accounts of the Einstein-Bohr debates. I'm sure historians would be frustrated by what I'm saying here. But Bohr would then point out that there's some way in which that can't quite work. So a very similar dialectic has emerged here. Okay, so let's take stock. Hopefully we have gotten a sharper picture of what black hole complementarity is. Hopefully you're at least somewhat persuaded that it's useful to think about complementarity as a claim about consistency, and that we
could at least distinguish between operational claims of consistency and representational claims of consistency or descriptive claims of consistency. And if we don't like instrumentalism in our philosophy of science, then we would prefer the descriptive principle over the operational principle. But recent literature has told us that operational complementarity seems to be much more successful, and the descriptive principle, as I have at least articulated it, can't be right. Maybe there are other ways of articulating descriptive complementarity. But let's ask, so let's say you are a realist. Let's say you're a scientific realist. So what do you say to all of this? Well, if you lean anti-instrumentalist, then the failure of the descriptive principle of complementarity is probably not too surprising, right? Because the information paradox was a paradox. It pointed out an inconsistency within our theory. So it's no surprise that that inconsistency keeps popping up if you take your theory representationally seriously. You can run, but you can't hide. But so if you want a new realist theory that will solve the paradox, at the very least, you'll want to take the success of the operational principle of complementarity into account, right? Just as if you want to give a statistical mechanical account of why perpetual motion machines are impossible, you'll at least want to take that evidence that the way designs of perpetual motion machines always seem to fail in some subtle way, that should be one of your pieces of information that enter into your theory building. So as a realist, you'll be unsatisfied by the literature so far, but at the very least, the operational principle success is one more datum into your theory building enterprise. And just sort of tentatively, let me suggest that because the operational principle of complementarity required a quarantine of Planck scale physics, this suggests that any potential solution to the information paradox that doesn't appeal to Planck scale physics might be sneaking in some operational principle somewhere. So in principle, I'm having in the back of my mind some recent solutions, proposed solutions to the black hole information paradox that are using ideas from holography and don't seem to be making any new claims about Planck scale physics. And my suspicion is that they're sneaking an operational assumption somewhere, but this is just a guess and I'm not arguing for that here. But let's say you are comfortable with operationalism. Let's say you're okay with instrumentalism. So is there a paradox left for you at all if you accept the success of the operational principle of complementarity? So what is a paradox? So Quine gave this famous explanation that a paradox is a plausible argument to an absurd conclusion. But if you're an operationalist, what does it mean for something to be absurd? Well, a conclusion is absurd for you only if that absurdity has some kind of operational consequence, right? So if you're an operationalist, you're going to tell me, I don't care about entropy curves. I don't care one entropy curve that goes this way, another goes that way. Tell me some experiment that forces me to abandon some principle of physics that I cherish, right? Tell me some experiment that violates quantum mechanics and then we'll talk. Until then, I don't believe that your absurdity is a real absurdity. But if operational complementarity is successful, then there seems to be no such experiment. That is, you can't quite do an experiment that will detect a violation of quantum mechanics. By the way, cards on the table, I don't lean operational, I lean realist. So this line of argument, even though it seems something that's important and should be taken into account, is not something I myself am fully on board with simply because I'm not operationalist, but I think the operationalist has a lot going for them in this context. So if you're operationalist and if operational complementarity continues to be successful, that is, you know someone is not able to identify some new experiment which will allow for the detection of violation of quantum mechanics, then there's no paradox left for you because you don't have an absurd conclusion. So it does you don't have an argument to an absurd conclusion, and so you don't really have a paradox. Thank you.
Thanks, Siddharth. Very, very interesting talk. So we have 10 to 15 minutes for questions. So I've already explained the rules. So anyone, okay. Jeremy Butterfield has a question. So Jeremy, you can go.
Thank you. Thank you very much for the talk. I enjoyed it. There's quite a lot of issues about the jargon complementarity and how it relates to Bohr that are around. But let me pick up on that last comment that for an operationalist, a conclusion is only absurd if it's operationalizable. I think that I'm no operationalist, but I think they ought to respect standard logic, and they shouldn't tolerate absurd conclusions if they're not just on the grounds that there is no experiment that manifests them. Traditional operationalists would surely normally accept standard logic. I agree with your general drift that the operational complementarity does better than descriptive, but that's partly, I would say, because it's less ambitious. Because if I caught you correctly, it was defined as no violation of quantum mechanics outside Planck scale physics, which is what you might call a reasonable expectation given the success of quantum mechanics, never mind the details of the black hole debate. And the descriptive complementarity was clearly ambitious because it said the infalling and the outfalling, or the interior and the exterior, are consistent with each other and with quantum. So it was logically stronger because it had a much more specific topic, really.
Yeah, so let me take those. I think there are two questions there, so let me take them one at a time. So the first question was about whether an operationalist should respect classical logic. So I'm not sure that, well, it depends. There are many different flavors of operationalism. But if I understood at least one prominent vein of operationalism correctly, scientific theories are basically instruments that help us predict experimental outcomes or organize our observations of the world. And just as a historical fact, in some contexts, being logically consistent has been quite helpful, but in other contexts, maybe it doesn't. I mean, we know that just our ordinary languages, all kinds of logical inconsistencies. Just off the top of my head, you can think about vagueness as, in some sense, violating classical logic, but they all seem to be perfectly powerful, perfectly reasonable and powerful ways of dealing with the world. And also I mentioned there's a historical record of scientific theories having inconsistencies, but people knowing how to work their way around those inconsistencies. So of course, I think they would like their theories to be consistent with classical logic, but I think they will give up classical logic, or they don't actually even think in those terms until you can show that that violation of classical logic results in some kind of experimental problem, right? Does that help at all?
Well, I don't want to take up too much time. I think I have a stricter historically justified definition of operationism as theory is reducible to observation, roughly. Any concept. This is you know, good old Bridgman, Bridgman. Every concept that you think is theoretical boils down, and then all of theoretical statements will be ultimately logically analyzable into observational statements. That is clearly cast in a background of classical logic, and it's not the same as instrumentalism, which is a wider, more general doctrine, which even allows non-linguistic construals of theoretical statements. They are some kind of tool or device for inference, but they're not propositions. On my operationism, theory is propositions, namely it's highly abbreviated observational propositions conforming to good old logic.
Right. So so this is.
I should shut up.
No. This is
other people talk.
Yeah. Let me just quickly respond to that. Is that I think, I think I briefly mentioned it, but perhaps I should highlight it more. Is that I mean operationalism in the sense that's closer to instrumentalism only because this is the language that's common in the physics literature right now. So they're not being historically precise. And I completely agree that there's a long tradition in the philosophy literature about what operationalism is starting from Bridgman, and I sort of try to say that that's not quite what I mean here, but I agree that, that's a different thing. Yeah. I can answer your second question, but perhaps if there's another question, I can take that, or I can answer Jeremy's second question.
Sebastian had a question.
Thanks for the interesting talk.
Thank you.
It was more of a remark. So part of what you are doing is trying to clarify the notion of complementarity, which I think is very interesting. It wasn't Susskind who invented this notion.
Sure, Etuve,
So there are these papers starting in 84 until 96 by Etuve, but also there are a number of papers by him and the Verlindes and some other people who brought in some ideas from string theory, basically. So the idea was that you could construct or could attempt to construct an algebra of operators at the horizon. Is where that basically the infalling and the outfalling and the outcoming observers had non-commuting observers with respect to each other and so on. So I think there's a closer connection there with quantum mechanics. And so that's my suggestion, that I think in clarifying the notion of complementarity, it would be interesting to take that literature into account also.
Yeah, no, certainly, I agree with you. I read your paper with Van Dogen, if I remember correctly, and where you discussed this, and that was quite useful to me. And it was just for interest of time and space that I did not discuss that. I think those kinds of results would also, because I argued that operational complementarity is actually closer to Bohrian complementarity is closer to operational complementarity. And those ideas, I think, are sort of trying to really just take the Bohrian idea of complementarity and translate it to the black hole context. So I would categorize them. I mean, you didn't ask me this question, but within this dichotomy, I would categorize them as operational complementarity. But thank you. Yeah, those are important precursors. I was sort of looking at a particular strand in the literature, but there is this other strand as well.
So the question?
Yes, my question is something about what told Sebastian, the fact that there's no commutation, as Marco and Enrico wrote in a paper, a post question about the possibility to make a distinction between these entities. So both no cloning, the relation of no cloning and monogamy is not so clear, and so in a certain sense, the score is 3-3 among between. The ontology depends. The ontology depends also on what happened to the observables of the three objects that are entangled. So it's not so simple. It is, I think, it is a bit naive to distinguish the three entities in the way that is normal in the case of this paradox. But Enrico perhaps can explain better the point.
Yeah, thanks. Sorry, I couldn't hear you fully, but if I understood you correctly, you're saying that it's a bit naive to just take a foliation that's smooth across the horizon and then say that, well, look, you have a state here and a state here, and you have a violation of cloning or monogamy. A more sophisticated way to do it would be to say, well, only one of these descriptions is valid at one time, and so you can't really have a description that crosses these two languages. And I feel like that's precisely my point. I want to be a bit naive in taking the descriptive complementarity, because I think sort of if you just sort of naively take your theories representationally seriously, then you have this contradiction here. And in order to make those moves about, well, look, you can only use one of these collections of observers at one time, that requires some kind of operational constraint, because why is it that we can't use both the descriptions simultaneously? Well, we'll have to say something about one experimental context versus another experimental context. And yeah, so I think sort of articulating the naive versus what is philosophically required in the more sophisticated answer is part of what I'm trying to do here.
So maybe I can just quickly follow up on what Enzo said, and we can have a short break. So, I mean, I see what you mean when you say that. So you want to do this basically, let's call it naive thing, even maybe it's not the correct way. I think what else I wanted to say, and I kind of agree with that, is that you cannot be too naive in a way. So basically, what the descriptive complementarity is doing is kind of sneaking in the way you phrase it, is that the description have to be in some sense independent of each other. So, for example, I can use what the unfolding observer is seeing, and I can just mesh it somewhat cleanly with what the exterior observer is seeing, and I get, for example, a monogamy paradox or something like that. While what seems to be the case is that, well, there are ways to solve, for example, the monogamy paradox and the cloning paradox that seem to involve the idea that this is exactly what you cannot do. And it's not that you cannot do that for operational reasons, like the operational explanation of why you cannot do that is the Arlo-Hayden construction that you mentioned. But there seems to be a let's say, descriptive reason as to why you cannot, in that if you actually try to construct the interior, for example, imagine you have a tomographic theory and you do something like bulk reconstruction, then you find out that you have, for example, things like islands. And then you find out that what was going on in the interior was not independent of what was happening outside. And so those two descriptions were not really independent in any meaningful way. And so the counting that you are doing that led to the monogamy paradox was not really there, because the two descriptions, in a sense, the two descriptions were not commuting. This is what I meant when I said independent. So it's not really a naive versus non-naive distinction. It's more a, do you assume that the descriptions are independent? What's going on in the exterior is independent of what's going on in the interior? Or do you not? Or should the descriptive complementarists remain silent on that and just do these calculations, their calculations, and find out?
Yeah, so if I understood you correctly, you're suggesting the following kind of idea, which is that, well, look, why do we believe, in a way, let's say you're in the exterior of a black hole, why do we even believe that there is this interior that exists independently of the exterior, right? Let's just imagine that there just is the world outside, and what we think of as the interior is just some delicate, encoded way of describing the exterior degrees of freedom, right? So I can sort of see that idea, right? That basically you're saying that when Alice, let's say the cloning paradox, when Alice sort of emerges in the radiation, that extremely complicated radiation state just is Alice in the interior, right? There's no really much more, there isn't this other Alice who's inside the horizon, who's carrying on a life independently of the radiation. The radiation just is the Alice in the interior. And I can sort of see this argument being developed. And I think the reason why I suspect that there's an operational idea even there, that let's say you agree that, let's say Alice in the radiation just is the Alice in the interior. Well, it suggests that you can signal, that Alice in the radiation can signal to you, right? Because in principle, observers on the outside have some kind of ability to access the radiation degrees of freedom. But usually, at least in the literature, what I get the sense is that the restriction on accessing those radiation degrees of freedom is again rephrased in terms of operational language, where they say, well, you can't do measurements that are too fine-grained on those radiation modes that will allow if Alice has to be able to signal to the exterior and Alice just is the radiation, then that signaling will have to involve exterior observers probing extremely fine-grained structure of the radiation. So maybe there's a way to escape that. I'm not saying I'm fully one way or the other, but I have a feeling that that an operationalism comes in even in that kind of picture. But maybe it doesn't. Maybe there's a way to escape.
I see what. So sorry. Are there questions for Siddharth?
Okay. Jeremy also had a second part of his original question, so I'm happy to answer that if.
Then we'll have a break then.
Okay. So Jeremy, if I understood you correctly, your second part of your question was, it's not too surprising that descriptive complementarity sort of underperforms operational complementarity because it just is more ambitious. And I agree with you, right? And I think this is sort of, the game is a little bit rigged in favor of the operationalist, because they don't care about taking their theories representationally seriously, and that gives them much more freedom to move around. I think so my suggestion, I hope I didn't give the suggestion that these are supposed to be like equal in principles. I think the reason I sort of brought out a descriptive principle of complementarity was just because in the literature I sense sometimes there's this confusion where people seem to be able to think that what they're doing is not operational or somehow not building in some kind of philosophical assumption, really. And I think what sort of setting out a descriptive principle and saying clearly the way in which, if you take your theories representationally serious, there's really just no way to hide from the black hole information paradox, right? You can't really get away from it. And so, that was sort of highlighting that point was part of why that principle was brought out. So, but I agree with you that there's a skew. Yeah.